the normal work instruction to get rid of problems in high-pressure die casting, then it's shooting faster, shooting hotter, and shooting with higher and higher pressure. And in Rheocasting, you go absolutely the opposite way. You shoot lower speeds. You add your pressure in the end, but the whole thing is you are trying to be laminar instead and use that shear force to get the melt to stay alive longer in your tool, basically.
Yeah, a laminar fill is the keyword here because everybody interprets if you have Rheocasting, you automatically have laminar fill. And I have to break it to you, that is not true. Just because you have Rheocasting written on the package doesn't mean that you get a laminar fill.
Hello and welcome to the Goldcasting podcast. Today we have a special edition concerning about Rheocasting, and as both me and Fabian are having a lot of questions about Rheocasting, how it works and is it stable and what is solid fractions and all these things. And sometimes we get a feeling that there's a lot of questions that people are thinking about, but they don't have a chance to get a serious answer. So today is today. All the questions you didn't dare to ask on Eurogas or wherever you met us. So on basis on what all of you out there have been asking us the last 2-3 years, here's a summary. We're going to go through it from A to Z. So we welcome each other to be the interview victims today as we work in this field. Right, Fabian?
Yeah, definitely, because every time there's a question, and especially as Rheocasting is not by itself, not a new technology. It started in the 1970s, and it's such a wide field what actually is Rheocasting. And yeah, many people had negative experience with the process. We will dig into that, where that comes from, why it is that way, and what are the key figures to have a successful Rheocasting. And yeah, I think we shouldn't do the introduction longer and just dive right in. And the starting point is basically how to see Rheocasting, because we know high-pressure die casting. High-pressure die casting is a beautiful, highly efficient process to produce many parts. But what we are seeing now is that for certain applications, we are at the limit what high-pressure die casting can do. And if you want to go beyond that limitation, then Rheocasting comes in. So Rheocasting is not an AI startup. It will not revolutionize the world. And everything will be done Rheocasting. No, Rheocasting is an addition to the high-pressure die casting process. It's a different melt preparation, and it expands the scope of high-pressure die casting. High-pressure die casting isn't going away. It gets more work to do, and I think that's more than needed for the industry.
Yeah. From my perspective, what I see with the customers and people using semi-solid casting is that they reach new fields on the market, and they can actually fill capacity with new parts, new applications, basically because demands are different when it comes to mechanical properties, LOU, sustainability, thermal conductivity, and so forth. So see it as a tool to bring to your high-pressure die casting to reach new business. That would be my summary. Very odd to have it in the beginning of the podcast, though.
Yeah, but I think it's keen. Also used another word, which was semi-solid casting. And to get our facts and figures right, so semi-solid casting is the headline where Rheocasting is one of the categories. The second category that falls into that would be Thixomolding or Thixocasting. The difference is that in Rheocasting, you're starting with a liquid melt and cool it down in the semi-solid or half solid, half liquid area. And then when you do a Thixomolding, you're starting with solid, usually chips or any types of small pieces, and then heat them up into the semi-solid area where you have the two phases present at the same time. That is basically the difference in the processing route. And as you're starting in Rheocasting with a liquid, it makes most sense to use Rheocasting for aluminium because you don't really want to have a liquid magnesium bath on the open air. On the flip side, when you do Thixomolding, that's ideally for magnesium because the tool wear on these screws is way too big if you use aluminium for that.
So, what you just have described is high-pressure die casting 2.0, add Rheocasting, but it's not golden paint. You have to keep your things together. Meaning, if you have a bad metal hygiene, if you have oil leaks in your machine, if you have a bad vacuum, etc., this doesn't work like golden paint and everything comes out of the machine perfect. You have to have your standard of making high-pressure die casting must be in place first. The homework done.
Yeah. So for many foundry, that means they need to upgrade their peripherals. But if you're already familiar with, for example, structural castings, everything you need is already in place. So Rheocasting doesn't require any big changes in that case. But you need to know how to build a proper tool. You need to know how to spray release agent. You need to know how to take out hot spots without spraying water on them, and how to get to good properties. And these are the things that are important. And if you don't have done your homework in high-pressure die casting, it doesn't make any sense to look into Rheocasting because it won't solve your problems. You have to get the groundwork in, build a solid foundation in high-pressure die casting, and build on top of that. So, for example, when people contact me saying, hey, we want to do Rheocasting, we have a part here. Then they show me an oil pan for a two-wheeler, for example. And then I spend 30 minutes in our call convincing them not to use Rheocasting, just to do standard high-pressure die casting, because it adds way more complexity and the application doesn't need it.
Nope. And then you're speaking a little bit of the disclaimer here. Rheocasting is not the golden paint. You have to master your high-pressure die casting. You got a picture here in this slide, which is very interesting, where you see an ingate and you see something like, I would say, a bed plate, and you see a big hole in it. And this is what you can find if you don't do the homework, and you still have to do simulations, you still have to do your engineering, your casting planning. But if you do, then you'll find interesting aspects of, I would say, again, marketing tool to reach new markets where this is the thing. So let's dive into a little bit more on the technology, Fabian.
Yeah, absolutely. And just at the beginning also, because what we are claiming for Rheocasting, and then you said, yeah, these two are talking, let's go and test it. And I will tell you right away, if you just take your high-pressure die casting tool, take it to a test facility for Rheocasting, that trial will fail because you never set up the tool for the process. And it had nothing to do with the Rheocasting process itself. It's just the setting is not ideal to succeed. That's like if you see me coming on a racetrack to define how fast can humans run. And then I do the 100-meter sprint. Maybe I'm getting around 15 seconds to 100 meters, and then I say, okay, I do it at 29 more times, and then it's getting slower and slower, of course, and then I will say and can determine 15 seconds, that's the maximum human speed. But you know it, I know it. If you are
it's
a
not
sprinter,
the world record.
No, it's not the world record, and I think every professional sprinter does that as a warm-up lap. Therefore, it's the same with your tool. If you are not prepared, you won't see the full picture. But let's go into the full picture. And I think the most important thing is that when we talk about Rheocasting is that we're not casting liquid, we're casting a semi-solid. That means that we have solid and liquid particles mixed together in one we call slurry. That has a behavior, basically, it looks like a bit of cottage cheese. And that's what we are casting in Rheocasting.
But it behaves like milk, right?
Exactly. That is the cool thing that we will get to in a bit, because Rheocasting uses Thixotropic properties. What it means, we'll get to that. But it's basically something we don't see in our everyday lives. The only thing where we can experience that is when you buy a new glass bottle of ketchup, you open it up and want to shake the ketchup out, nothing happens. And you shake it and shake it and shake it, and as soon as it starts to flow, the half plate is full of ketchup. Ketchup itself is also Thixotropic properties. As soon as you apply the shear force, as it starts to flow, it flows very well. Before that, it doesn't flow. And that's the same thing with the slurry. It needs some sort of shear forces to act like milk. And a high-pressure die casting machine with a narrow cavity, the plunger behind it, pushing it in, that's the perfect shear force generator, and that's why it works so well on high-pressure die casting.
And the interesting thing, if I look, you said something about if you take a tool and you go try Rheocasting, then you fail. And another interesting aspect of this is that, people try to get something that looks like a semi-solid. And the problem is that if you start to look like what you think is a semi-solid, like a porridge, then you're way too high in solid fraction. The second thing is that the normal work instruction to get rid of problems in high-pressure die casting then is shooting faster, shooting hotter, and shooting with higher and higher pressure. And in Rheocasting, you go absolutely the opposite way. You shoot lower speeds. You add your pressure in the end, but the whole thing is you are trying to be laminar instead and use that shear force to get the melt to stay alive longer in your tool, basically.
Yeah, a laminar fill is the keyword here, because everybody interprets if you have Rheocasting, you automatically have laminar fill. And I have to break it to you, that is not true. Just because you have Rheocasting written on the package doesn't mean that you get a laminar fill. For the laminar fill, the solid fraction is key to that. So if you have 0% solid fraction, so you're casting conventionally, you always have that turbulent fill. And now let's add 15% of solid fraction. So 50% of the material is already pre-solidified when you use it. Yes, you see the first effects of semi-solid, but still the filling behavior is still fully turbulent. There is no difference. Therefore also the quality expectation is nothing different in high-pressure die casting. Most of the time you get to the same quality results as in high-pressure die casting, but you can reduce the machine size a little bit. Maybe there's one porosity that gets now a bit smaller, that it fits the specification, but it doesn't change your world. It starts when you get to a higher solid fraction, something around 35% and above, that you have so much solid fractions that you can fill a tool in a laminar way that it doesn't give you that turbulent fill. It really goes through laminarly, but with 35% solid fraction and above, you also have to modify the tools, because if you have a normal gate, you just squeeze out that slurry, this liquid goes in, the solid stays behind the gate, and then you have a terrible casting throughout. And that is why most trial castings really fail.
Because of the gating. Yeah, the gating and everything. And you have a very nice picture on what you just said, where you see the different solid fractions in simulation, where you have a couple of cores going into the cavity. And you can actually see that 35%, and then the magic starts.
Exactly. And there's also what isn't shown in that picture. I call it the dead zone. That's between 20 and 30%. Where you have that constant switch over between laminar fill and turbulent fill, and that is where you 100% produce scrap parts if you slide into that with your process.
The zone of death, you hear that? Yeah.
Yeah, but it also means when we're talking about that we need 35% solid fraction to have that laminar fill, that also means we need to pre-solidify 35% of our alloy. And when you're taking, for example, an ALSE10, you are so close to the eutectic point that your solidification interval and your primary alpha phase is not enough to get to that 35%. So you need to be, when you see it in the graph, below 7.5% of silicon or 8% of silicon to get to a 35% solid fraction. Otherwise, you're pre-solidifying the eutectic phase, and then when the eutectic reaction starts, everything solidifies, and you not really see any of the aspects in Rheocasting.
Yes, but from a commercial perspective, there's actually a tweak to this. If you look at the graph like this, you will say that 8.5%, no way, you will not have the solid fraction enough. But if you're looking at an A383 or 226 or 46,000 and place them inside the specification and cast with Rheo, there are so many other additives into the alloying elements like iron, manganese, magnesium, etc., etc. And all these different atoms helps to expand the process window. So what I'm saying is that this table is absolutely true, aluminum silicon, but in practical life, if you have a part in 226, A383, 46,000, something around 8.5%, go ahead. It will work.
Absolutely. The key thing is that the other elements, especially copper, opens up that solidification interval to get to the 35% solid fraction anyway. And that's basically the key thing. And we will show also a graph where we have different alloys from 2.5% silicon to 7-8% silicon in a range where you have different properties for these castings. And that is best when you see it on the screen when you're watching the video. We don't go into every alloy in that audio feed. But the key thing is basically, and that is also a big advantage in Rheocasting, that the castability isn't defined by your silicon content, as when you see it in high pressure die casting. An LSE 10, 11 casts well. You get castability issues when you go to an LSE 7. In Rheocasting, an ALSE 2 casts the same way as an ALSE 7, ALSE 8. All of them have the superflow behavior because of the Thixotropic behavior and laminar fill. And that makes it so interesting to also try out these different alloys, different silicon contents. But I think that also brings us to the next point, because we know now which alloys we can use. Now the big question is how to make that slurry, because we want to have the 35, ideally up to 45% solid fraction. Never go in the zone of death and don't have a too low solid fraction. And when we look especially on the patent side, last time I checked, I found 87 different patents for various processes in Rheocasting. And
that is a big pile of patents.
That's a big pile of patents, and there is so much going on. So it's understandable that it's a challenge to see what are the differences. And here's the quick run through, because there is basically, we can put them in the pie charts, have 86 of these patents on one pile and one patent on the other side. And the key thing is that in Rheocasting, as it's not new, there were trials going on for decades and nothing succeeded. And the big thing why it didn't succeed is basically temperature control. If you're running in a laboratory, you have one batch of metal and casting that same batch every day, you don't see the issues. But when you have a series production running and have these small little changes in the chemical composition, 0.5% silicon there, more, next day it's a bit less, then suddenly your liquidus temperature changes more than your temperature between 20% or 40% solid fraction. And we can see the difference in the part very quickly. You cannot see it in the process, in the slurry making, but you see it in the part. We will show it on the screen that for 20% solid fraction, you have that turbulent fill, you have entrapped air, and in the heat treatments you have blisters. Then going back into the melting furnace, at 40% solid fraction, you have that perfectly laminar fill of the casting, and that's what you want. And so you need a process that is absolutely gives you the same condition every time, and that's the Rheo metal process with its enthalpy exchange mass, and that makes it that only process that is not temperature, it's enthalpy controlled. And I think, Staffan, you can tell us more about that process.
Yeah, basically, if you control the nucleation and making the slurry by knowing how much solid material you actually put into a cup of molten metal, you reduce the influence of surrounding temperatures. So as long as you know what you have in your holding furnace and how much solid material you have and how much you pick up in your ladle, you're home free. And we did corner testing on this with plus minus 5 degrees in the holding furnace. And the outcome was, after, I don't know, quenching how many hundreds of portions of slurry, was 3% units. So meaning that you had 36, 37, 38% solid fraction. It's not a very big variation. And what this means in practical life is that you have something that is stable. You can open the door to your foundry, it doesn't affect anything, and you can do a lot of things. But the laboratory developed processes are always temperature controlled, and keeping track of your temperature in a foundry is actually very difficult.
Absolutely, and we can show you the pictures again and let you guess what is the temperature difference in that same slurry between 20% solid fraction and 40% solid fraction. We will give you a few seconds of time to think about a number. You got your number? All right, then I will tell you the number. It's 0.8 degrees Celsius between these two slurries. And that's with the same batch. If you have a variation from one melt to another melt, the changeover in the liquidus temperature is way bigger than that change in slurry. And imagine 3 o'clock at night, your night shift has to adjust the process in the 10th of a degree. That is impossible. It doesn't work.
No.
But so you're doing one shot with 20% solid fraction, and the next day you're shooting with 50%, and you have the constant change over what you're actually producing. And therefore, you have a totally inconsistent quality output. That doesn't work. And then with your Rheo metal process, there you have a 22 millimeter height difference in that EEM, in that aluminium ice cube. And as in a gravity die, you always fill that to the brim and you cut off the ingate. So you're absolutely rock solid. You have different temperatures, yes, but you always have the same slurry condition, and that's the key thing for the casting process.
And I think if one wants to go deeper on this, you should take your old physics book and you should check up the enthalpy, the energy of melting and solidifying alumina, which is so much higher than the energy needed for increasing the temperature 1 or 2 or 5 degrees. It is massive, and aluminum has this, also magnesium as a matter of fact, and this is why they become extremely stable slurries. The only thing that happens is that alpha grains grow, but the temperature is the same. I don't know how many thousand times I had a question, okay, what is the temperature now? We have measured this 10,000 times. It's always A356, 618 degrees Celsius. All right, that is what it is.
You always, for an LS7 MgO3, it's somewhere around 610, 611 degrees. You end up always in these ranges.
Yeah. You can calibrate your measurement device by checking.
Yeah, but you have a bit of a variation from a bit more silicon, bit less silicon. But you have the same solid fraction, because that's why these temperature measurements don't work. And the key thing here is then to add to that also that, for example, when you take, for example, microscopic image, what you're just describing is that you produce that slurry, you have your primary alpha phases produced, then you cast it, and then you solidify, of course, on top of the tool steel, but the surface area of these globalites is so much bigger than the surface of your part that most of the solidification is happening on top of that. And the latent heat, so the energy difference between the liquid and the solid form, goes back into the remaining melt. So your slurry doesn't lose the temperature. It's more like casting a pocket warmer. It maintains a temperature throughout the travel into the cavity, and that's why you can reduce the metal speed so much that you get into a laminar fill.
I would like to change the subject to alloys. You see this table, and again, all these misconceptions that you see out in the market. But if you look at the chemical composition, you'll find alloys from 2.5% silicon up to actually 9, the A383, for example. And a few words on them. You see something called Rheocool, Rheogreen. These are developed inside Comtech for certain applications, especially for either telecom or, I would say, not traditional car makers, because there is no standard here. The reason why they're called Rheogreen and Rheo Standard is that they have extreme low carbon dioxide emission rates from the production of the alloys. 100% recycled. But then you see something called EcoMelt, and you see the standard here, A356.2. Very good for sustainability, but take a look on the numbers of the properties you can get. This is like a designer's toolbox. You can have as cast with super elongation. You can do a T5, you get a nice material. But if you really want to have it really strong, you do a T6 and push up the yield strength, ultimate tensile strength, and also elongation. Now, having said that, why is this important in Rheocasting? Well, first of all, castability is good in low silicon contents like 7 or 5 or 6 or 2 or 8.5. And then the laminar flow, no entrapped air, meaning the T6, normally if you take a part with porosity and make a T6, it will look all blisterly. Now it doesn't, because you don't have dust porosity inside your part if you've done everything right. So I just wanted to mention this, that if you look at the table like this, you see a lot of different things. You see alloys with nickel for high temperature stability. You see alloys with super low silicon with very high thermal conductivity for heat sinks. You find A356 types for load-bearing applications where you can kill low-pressure die casting and actually steal more market. So there's a lot of alloys, and this is the second toolbox. You have the low porosity. Yeah, sure, that's great for leak tightness, for T6 and welding and all that. But then you have a new set of alloys where castability is high. And if you look at the aluminum silicon 7 MnMg, like the Oral 5, for example, we actually cast these 4 meters of flow length. Try that in high pressure die casting. I think it will be difficult. And we did it on the first attempt. So again, alloys is 50% of the reason why the porosity in laminar flow is the other 50%.
Exactly. And also when you're thinking about or heard, oh, you need specialized alloy that you only get from one vendor. Staffan talked a lot about the A356, which is basically the most common casting alloy in the world. Every sandcaster uses that alloy.
Yeah.
So you get that wherever you are.
In tons, yes.
And also, if you think about that alloy is specified at every OEM you can think of, because everyone has castings in that alloy, so there is no huge material specification to go into new projects. And that's, I think, is the key thing here for these projects, that you get the perfect no air in. And the extreme of that, what you can do is, what about helium tightness? Because we're now seeing that with the EU F-gas ban, that the standard R134A compressors have to be phased out for new platforms. What do? If you want to cool a battery and also the interior, you need something way more efficient. Otherwise, it goes towards your consumption and therefore your reach and range. Yeah, a CO2 compressor can just plug in this basically there in that system. It uses the same setup. You can heat and cool in the same circuit, and now you have triple the efficiency. But you're not operating at 15 bars, you're operating at 150 bars or 160 or 180 bars. And there is no way that high-pressure die casting with its turbulent fill can hold that pressure. Impossible. Even with impregnation, it doesn't work. And you can't even impregnate these things because they have to be welded shut. But Rheocasting, without impregnation, perfect laminar fill, that thing is leak tight, tested at 180 bar helium level tightness. Ideal thing. These run in hundreds of thousands of pieces per year. Perfect to get new business in, even with high volume production. And I think that shows you how extreme the applications can be for Rheocasting.
Yeah, then we had that segment, alloys. We are making an example of this delivery truck hinge pillar that we can see in a picture now. And it is pretty interesting because this part was originally high pressure die casting in a 3,000 ton die casting machine. The length of the parts is 1,440 millimeters. It's pretty long, I would say, like a longbow, basically. Contains numerous places where you have a thick material and then thin material. So 3 millimeters up to, I think it's 26 millimeters, the wall thickness in some places, because of gluing, bolting, and welding. And you can derive a lot of interesting stuff around this, but let's talk about machine size decrease, because now it's a 1,600 ton machine from 3,000 to 1,600, and then an explanation is needed, right? We have to elaborate this a little bit. Why do you use smaller die casting machines? So of course this was a great success. It became the NADCA winner in the trade fair in 2022 because of sustainability, but also the properties it received and all the things and aspects of the part were honored by this, of course. But besides this, a smaller die-cast machine, there's two effects here. Number one effect is, of course, you see the projected area. If you have all these overflows, if you have all these in-gates, you have a bigger projected area around the part that you actually have the part itself. In Rheocasting, we work with much lesser of gatings and overflow. So we take out projected area. So that's effect number one.
And the second effect is also that you take out mass in the gating, in the overflow system, so it's less material to melt.
Yeah, that's an important factor. But the second thing is also that when you cast in high pressure die casting, every time the melt hits a wall, it changes direction. But after that wall, it goes to another wall and another wall and another wall. And if you measure this very, very carefully, you can see that you get a knocking effect, that the pressure is 0, full, 0, full, 0, full, 0, full, 4, 5, 6 times in a structural die casting. And that means that you kind of knock up the tool. So you get the flash or the tool opens. So locking force is required to keep it together. That former effect is actually examined by the GTK, and that is just what it is with a measurement, minus 30%. So if you combine minus 30% from the knocking effect and then also with the projected area, you get a heck of a decrease of the die casting machine you need. So our problem when developing parts is more, do we have the tool table that is big enough for the tool? We never speak about the locking force, But we have to speak about the locking force to sort things out with our customers. What kind of machine do they have? Because then we know that, okay, with that locking force, you probably have an injection side that is that strong and can shovel in the material in the speed we would like to have it, and with the pressure also, by the way. So machine size reduction is not any secret Harry Potter magic. It's lesser projected area and lesser with knocking effects from the metal going into your tool. End of story.
That seems really too good to be true, but as you see it in these examples, it's actually true, and we've seen it for so many other applications where you have, for example, because of porosity issues, oversized die casting machine, and then you do the same machine size, a two-cavity tool of the same part in Rheocasting, because you can reduce it down in projected area and then you have the double efficiency. And that also has a massive impact on your hourly rate that we see here, that usually can reduce the machine size by 20 to 30%. And then when you compare the smaller machine plus the investment in the slurry maker, of course, for the smaller machine, the hourly rate difference is not that big because in relation to the machine price, a slurry maker is relatively expensive. But if you get in the middle segment or in the large tonnage machines, the investment in the slurry maker doesn't really fall into account here.
But the interesting thing when you start to look at the cost decrease using Rheocasting, you might think this is a nice add-on, but this is actually very often the big portion of the saving over a 5-year contract for a high volume production. It represents 40-45% of the saving in a typical drivetrain product. It's actually the investment cost and depreciation of your machine over the years. So not having to buy a, 1,600-ton machine and do it with the 1,000 or 1,200, it's actually ending up after 5 years to be the big saving. Very often.
Yeah, that's a great saving if you don't have to spend money, and also you can move around certain pieces from larger to smaller machines depending where you have the issues to find capacity. But it's not the only saving that you can get with Rheocasting. Another big saving is that you also have the tool wear, which is low because you have that laminar fill, lower metal speeds. The slurry is 100 degrees cooler. So you have that are way gentler with your tool. Therefore, you're between 60 to 200% longer tool lifetimes. And that is something also which you see in per shot cost reductions quite a lot. Also, what often happens is we have a complex part, you have a very hard short curve for high pressure die casting to fill it quickly, to don't have too much porosity. That is a high tool wear application. And then you start to see these heat cracks, and then you have 2-3 people standing behind the machine grinding them off. You don't see that in Rheocasting.
That's a slippery slope. And also this with wearing out tools. If you're not running 5 million parts a year or 1 million parts, every time you need to ask your customer for a new tool, it's actually a business risk. Are they happy with you as a supplier? They're investing maybe 200,000 in a new tool now because after 3 years you have worn it out. And then the cost of introducing this new tool with all the bells and whistles and everything that has to be done on the tool. It's not that nice. But again, talking about this hinge pillar now, another aspect I would like to give, and now if you're working structural casting, you should probably listen pretty carefully, because there are a couple of things that happens when you use Rheocasting, and we have a picture here with a table that shows yield strength, tensile strength, and elongation. And if you start to look at the numbers of this, you see that they are very, very centered. Meaning that the spread of the numbers, the standard distribution of your numbers is very, very narrow. So this takeaway, why is this important then? Well, with Rheocasting, you get the same properties in all directions. If it transverse the flow length, flow direction, or if it's aligned with the flow direction. And also that standard deviation is very low. This is good news for everybody working topology, which is everybody. And topology means that you take a computer and you simulate your casting, the basic first design of your casting. You tell the computer, okay, we have a weld here, we have these forces acting on it, please suggest something. And then the computer do the math and then describes this is the perfect shock tower, for example. Problem is, the computer cannot in a reliable way work if it's not the same number of elongation, for example, or yield strength. And here you have a problem. So to make more lightweight, to make more efficient cars, to save weight on the complete assembly, everybody is needing to use topology, which this is called. And if you cannot count on the numbers, how can you do it? So having these kind of numbers in all directions with a very small standard deviation, as you can see in the picture, is super important. And this is why Rheocasting is that popular when it comes to structural castings.
Exactly. And for structural casting, the worst thing that can happen is that something goes wrong in the process, and then you suddenly go from 10% after heat treatment to 2% of elongation. And when the customer finds that out, and usually find out in a crash situation, you're on the hook and you really cannot control it. But in Rheocasting, you have these uniform properties, and when you do your regular shift-wise testing, then you can be sure that you really have the properties everywhere. And that's what the picture shows over several days of production, that you have that process stability.
So if you're expecting a delivery from Amazon in a delivery truck, you can at least be safe that the door will not fall on you.
That is hugely important, what you just mentioned, Staffan. And I think, especially when we go to the extremes of our casting worlds, and then we are, of course, in the Gigacasting sphere, where you really have these 2-3 meters of flow lengths, and you probably need very good mechanical properties at the end, because that's the end of that casting is where the people crash into you. And you don't want to have them sitting on your backseat. You want to have the casting taking up the energy with good properties, and therefore Rheocasting is perfectly suited for that, to get really the long flow lengths. Another thing is that, of course, that we can also in that application reduce the machine size, take a bit of the edge off in that investment case. And once we did the calculation, when you go from something like 8,000 ton to 6,000 ton, that makes around €9 per casting. That is nice. But the big savings, and here we now have a total cost of ownership view on the situation, is basically by extending the tool lifetime. The tool life is super critical in these large castings. So you have to go very quickly into the casting and have 50, 60, 80 kilograms of liquid metal rushing through that ingate, going to the end of the filling. That is a very high thermal stress. That is a lot of erosion from that flowing metal. And the tools are highly expensive. So changing them all the time, having a new PPAP done all the time, that adds up very quickly. And when you have something that is way more gentle, that's designed for long flow lengths, and you get 60, 75, 100% longer tool lifetimes out of your very expensive tool, that is a massive cost saving.
The word of the day when it comes to gigacasting is I cannot sit here and bribe about all the volumes that being produced. Rheocasting is entering this field from smaller parts that are in production, not only the Amazon truck. We see others also in Asia, North America, and hopefully soon in Europe. But the discussion has shifted. In the beginning, it was the castability of aluminum silicon 7 because people wanted elongation and get rid of the T6 treatment. Today, we are discussing more with our customers in trials and developments about the OEE. It's exactly what you're saying, Fabian, the pressure on the equipment. I mean, you pour maybe 60, 70 kilos on the same spot in your shot sleeve. So stopping your machine for changing your shot sleeve is quite an operation. Can you prolong this with 4 hours? Yeah, okay, then you go from 8 to 4 hours. Another thing is that if you look at the spray cycle, you pour in 60 kilos this fast, and cycle time is something that actually is very important because the investment of a 6,000 or 9,000 ton machine is very, very high, and to operate them basically. So speak about the cost of ownership. These things are yet to be found. How much does it affect the stopping time and the number of stops when you run these big machines? But it's going to be very interesting because look at the world. I mean, it was like 100 contracts and 3 machines were actually operative. Now the figures are changing and more people are using their equipments, and more cars are coming out with gigacastings. And now we see also the surge for production data, production numbers, and how to manage these massive investments. And Rheocasting could be a tool, cannot elaborate too much, but hopefully, and you will probably see it growing from the small parts to the big parts. So if you look at the table, what do you have? The cost of ownership, or landed cost of a part, because this is pretty much what it ends up to. You have the machine size, which I claim is one of the biggest drivers, because all the things around the machines. So 30 to 50% smaller locking force, and that of course hits the investment directly. You have the tool life length. Depends on, and why is it in percentage, you might ask? Well, if your customer is asking you to use a very low iron content alloy, it will be a chemical corrosion. It will be much better with a Rheocaster, but you cannot promise 200,000 shots. If you today are making 30,000, maybe you do 60. But again, you got the chemical corrosion instead of the dynamic heat load, I would say. Longer flow length, lower porosities.
Also adding to the topic of the tool lifetime is that when you're still pouring liters after liters of water onto your tool to cool it down, Rheocasting doesn't have an effect on your tool lifetime because you destroy it anyway by pouring cold water on it. So that doesn't really make sense. But if you're having a good thermal management, then Rheocasting can give you the additional benefit.
Absolutely. So now in the table, the examination here is about a rear floor, I think, 93 euros. And you're doing, I don't know, 700,000 cars if it's a normal plant in 3 shifts. 700 times 93 euros. I mean, it's a big money in it. But I'm coming back to this, that on the other side of the wall, you're assembling cars, and the car is, 400,000 euros or 700,000 euros. And every time you miss a shot, you actually miss a production slot for making one of these cars. Think about it that way. Then all of a sudden, putting in something that might affect your OE in a good way, might be worth it. And then as a benefit, you get everything that you see on the table, because the cost of not producing a car is actually higher than 93.41 euros. Just a reflection.
Yeah, that's something where we, from guys from the foundry industry, really have to step away from the measurement of the cycle time and go into what is actually then impacting the overall number, and that is the number of sold cars. And if you have a casting that is in a bad quality and you're directly delivering into the production line, that car will not be built. Or in the worst case, it will be a recall, making it way more expensive. Therefore, why not implement something like Rheocasting, where you have the higher assurance that you get a good quality casting out even after 2.5 meters of flow length?
But how do you do a recall for a body in white part?
Scrap the car, give the people a new one.
You. I mean, it's actually impossible to do something about it afterwards, I would say.
No, you can repair these Gigacastings, of course, in certain ways, but in a recall situation, nobody accepts a repair. You're entitled to have a new car. That's what you're getting.
Yeah, exactly. So basically, now we have gone through what people are asking about, the stability, what alloy to produce, where are we, can you do leak tight? I think we went through the whole circle, didn't we?
I think so as well. But there is way more that you have to ask and you want to learn about Rheocasting. And for everyone who wants to dig way deeper into that, now comes a commercial from Casting Campus. And from me, basically, that I have a course called the Rheocasting Masterclass, where you really learn everything in detail, how it works, and you become that Rheocasting expert that can tackle the first projects in that process. So if you're interested in that, contact me, go on the website and register for your spot.
And I must add, what I understand is that pretty many that are in this class comes from companies that are operating Rheocasting, which makes the discussion among the group of people so valuable. Because if you're thinking about going in this direction and you sit in a digital room with people that are sharing the benefits and the hurdles of semi-solid casting, and they have been running this for 3-4 years, I mean, then you actually get an even better feel for it.
Absolutely. You have the people that are interested, you have the people that are already using it, and you have the people that are looking to buy Rheocasting parts, all in the same course, in the same class. I think that's a great opportunity.
Then you have the crème de la crème. You also have people from the buying side, I've heard. I don't know any
Yes.
names, but I understand that people that needs to buy this stuff actually goes to this class to understand what am I buying. So yeah, sign up, guys. Make my life happier. It's not Comtech running it, but it's a great thing for us to see this happening out there in the market.
Thank you for that. And I think then we're at the end. Thank you for listening. I hope you learned a lot, and let's start a conversation.
And I would like to say it like this. Never stop asking questions. We will be happy to make more episodes based on your questions. If you're curious,
Absolutely.
you find out things. If you find out things, you become successful. That is what I believe in. So never stop asking. So thank you for this time. See you in the next podcast. Sayonara.
Goodbye.
Hej då.